polygenic overlap with MiXeR. Today we'll explain to you what this is all about, how to run MiXeR software, and how to interpret but not overinterpret the results. Let's get right into this. To understand the MiXeR method, we need to understand the polygenic overlap concept. Let me give you 4 examples. Example 1, 2 traits that are genetically correlated. Think of schizophrenia and bipolar disorder. On this diagram, you have 2 traits, each with 3 causal variants, shown in the red color. 2 of these variants are shared between traits, as reflected on the Venn diagram here on the left. The number 2 in the shared gray area indicates shared variants, and number 1 in the colored area indicates trait-specific variants. Hope this makes sense so far. Furthermore, both shared variants drive the risk in the same effect direction. They are increasing the risk variance. Clearly, this is an example of polygenic overlap with positive genetic correlation. Example number 2. This one looks very similar. Let's take a moment to locate the difference between the 2 figures. Here, one of the 2 shared variants, this one over here, has changed an effect direction, and it's acting in an opposite direction for the second trait. As a result, the effect of 2 shared variants cancel out, and we have a 0 genetic correlation. This is a scenario that we are targeting with a MiXeR analysis. But here is what Wikipedia has to say on this subject. A genetic correlation of 0 implies that the genetic effects on one trait are independent of the other. This is a false statement. In this example, we have 8 variants in total. So what are the chances of sharing 2 out of 3 variants? This is quite low. And in a real genome, the total number of variants is much larger, so sharing causal variants is unlikely to happen by chance, regardless of whether they have consistent or opposite or mixed effect directions. Here is example number 3, with 2 truly independent traits that do not share causal variants. And we have this disjoint Venn diagram with 2 causal variants in each trait that do not overlap. And finally, the false example shows the difference between mixed effect directions and opposite effect directions. Let's say if all of the variants are acting in an opposite direction, like in this last example, we have a negative correlation. But if shared variants are split 50-50, or if they are a mixture, then we have a genetic correlation close to 0. Note that all 3 examples shown here are examples of polygenic overlap, but only one of them, in the middle, is an example without genetic correlation. Here are all of the 4 examples together. Let's reiterate. We are talking about the genetic overlap with positive correlation, without correlation, or with inverse correlation, and finally, no genetic overlap. And MiXeR is aiming to distinguish between these 4 scenarios. So why is it important to study polygenic overlap? Because cross-trait relationship doesn't always boil down to simple correlation. Let's look at the relationship between schizophrenia, bipolar, and intelligence from a large study in Sweden. 2 plots here show an incidence rate of schizophrenia, it's a left figure, and the bipolar on the right, as a function of the GPA score which captures schooling performance. For schizophrenia, these 2 variables are negatively correlated. The incidence rate of schizophrenia declines with better schooling performance. But for bipolar, there is no linear relationship, and the incidence rate of bipolar is associated both with poor and good performance. Looking at the corresponding genetic correlation, this translates to a negative correlation of -20% between schizophrenia and cognition. But for bipolar disorder, the genetic correlation is very close to 0. MiXeR aims to find such nonlinear relationship between genetic risks of the 2 traits, similarly to nonlinear relationship between phenotypes that are already known from epidemiology. The connection between bipolar and cognition shown here may translate to a polygenic overlap of the genetic architectures, despite 0 genetic correlation. So how does MiXeR work? As input data, MiXeR uses GWAS summary statistics and an external reference, for example, Southern genome, to get the LD structure. No individual level data is required to run the MiXeR analysis. Then I take the 2 sets of GWAS summary statistics as shown here, and for a given MiXeR model, as shown on the Venn diagram, we compute what's called likelihood. It's a number that describes how well the MiXeR model fits the empirical data from a GWAS. Then playing with different Venn diagrams and different correlations, we can search for the one that is as much compatible with observed GWAS data as possible. So the one that corresponds to the minimum on the log likelihood curve will be the one that is the best fitting MiXeR diagram. But there is a challenge. We need to account for the linkage disequilibrium, as illustrated here by this locus zoom logo. You remember that on GWAS Manhattan plot, its locus is represented by a pile of associated SNPs. So when two genome-wide significant loci overlap between traits, how do we know whether the underlying causal variants are shared or not? To answer this question, MiXeR incorporates a comprehensive model of the LD structure to unravel its effects on GWAS z-scores, and it aims to estimate the true number of trait-influencing variants. In a way, this is similar to fine mapping techniques, where we aim to find a specific genetic variant that drives the signal in a locus. But MiXeR doesn't aim to find the location of trait-influencing variants. Instead, it aims to estimate the total number of those variants using a statistical model. But for interpretation of the MiXeR results, it's important to distinguish between terms genetic variants associated with a trait, which depend on the LD, or causal variants or trait-influencing variants, which are not dependent on LD. The main results of the MiXeR analysis are shown on this slide. It includes the Venn diagram, the negative log likelihood curves, and the univariate and bivariate tables. We've talked about the Venn diagrams before. The numbers here are in thousands, meaning that for schizophrenia and intelligence, we've estimated 100 variants specific for schizophrenia, 1,600 variants specific to intelligence, and over 9,000 shared between these traits. And the genetic correlation is negative 25%, as we already discussed. What about log likelihood curves? Horizontal axis here go all the way to the 10,000 shared variants, but it starts from 3,000, not from 0. More on this in just a moment. Each point on log likelihood curve corresponds to a certain MiXeR model. The point on the left corresponds to the MiXeR with the lowest polygenic overlap, those disjoint Venn diagrams that we saw earlier. It's also on the right, the models with complete or high polygenic overlap. And the lower the value on the curve, the better the MiXeR model fits the observed GWAS data. So in this extreme example, the model with 9.6 thousand causal variants is the best one according to the log likelihood curve. Let me show you a few more examples. Here, I think they're self-explanatory. In the first diagram, we have the minimum all the way on the left. Therefore, the best fitting MiXeR model is no overlap. The second one, the minimum is all the way to the right. So we have a complete overlap. And the last one is a partial overlap because we have a clear minimum on the likelihood curve somewhere in the middle. And let me point out one tricky detail. As I mentioned, the horizontal axis here goes from 3,000 to 10,000. So it doesn't start from 0. This is because the log likelihood curve are built along the overlap parameter with all other parameters being constrained, including the RG parameter. In this example, the RG is negative 25%. Therefore, we already know there must be at least some causal variance. And it turns out that if schizophrenia and intelligence have less than 3,000 shared variants, then there is no way they can have a 0.25 correlation. Therefore, it's not possible to stretch log likelihood curve further to the left without reducing RG. Also, you may notice the dashed lines here. Those are the 20 log likelihood curves built from 20 independent reruns of the MiXeR model, each constrained to a different set of SNPs, to see whether SNP selection has an effect on the result. If you see the overall curve consistent across these reruns, then the results are trustworthy. Otherwise, if there is too much noise, then there is not enough empirical data to support the MiXeR model fit. And let's go over the results in a table form from univariate and bivariate results. The exact parameters are described in the documentation, or should be described. Please let me know if anything is missing. And once you get those tables, it's important to pay attention to AIC or BIC values, which stand for archaic and Bayesian information criteria, respectively. They assess whether there is a significant signal in the GWAS data to support the MiXeR model. A positive value indicates that AIC or BIC does support the model. And BAC values appears to be overly conservative, and I suggest to report AAC values unless you see too much noise on the log likelihood curves. Now let's go over some practicalities. How to run the MiXeR software. The first link here provides the original software package and its documentation. But now there is an easier, most up-to-date installation procedure in the Comurment containers repository. It includes a quick synthetic example on an artificial data and a real-world example between schizophrenia and cognition. So the basic getting starting instructions is, so to get started, you just need to clone this Comurment GitHub repository. But know that you remember to activate Git large file support or Git LFS before you clone. Then you need to process your summary stats. And MiXeR required to have marker name, chromosome, base pair position, alleles, sample size, and z-score columns. This has to be tab separated, but it's okay to have columns, to have extra columns. You also need to remove the MHC region. When SNP column doesn't match the reference, MiXeR will automatically match your SNPs with reference using chromosome, base pair position, and the alleles. So for instance, with this summary stats, you do not need to translate the SNP column into the RS numbers. You just need to turn the summary stats into this format. Once you run the MiXeR, it's important to double check how your summary stats were interpreted. If you look at the log file, there should be a detailed section explaining how many SNPs were picked up, how many were removed, etc. This is a MiXeR script that runs the model fit. Note that all of the reference data is already provided in the Comurment repository, so you do not need to generate the LD structure nor the SNP selection. Here we are running the fit command twice, once for each trait, followed by fit2 command for the cross-trait analysis. If you have more than 2 traits, you probably want to split the scripts and finish all of the univariate analysis first, and then to proceed with all of the pairwise combination for the cross-trait analysis. The test commands here are used to produce QQ plots that we haven't discussed today. You may omit them and keep because they don't take too much time. Know that these are array jobs that are executed 20 times to assess stability of the MiXeR results. Also note that they are not reruns across chromosomes. So the @ sign, a placeholder for the chromosome label, should stay as it is, and MiXeR software itself will replace it with the 22 chromosomes. With 16 cores, it takes about 3 hours to complete. So in total, you would need maybe slightly about 1,000 CPU hours for a pair of traits. But the scripts to combine and visualize results are non-CPU intensive, and it's generally okay to run these commands on a login node. So to conclude, here are some caveats and limitations. First, watch out for the AAC and BAC or the log likelihood curves. If you see negative AAC or if you see too much noise on the log likelihood curves, then the sample size of your GWAS is not sufficient to run the MiXeR analysis. We also talked about causal variants, trait influencing variants, pure effects not induced by LD, or variants with non-zero additive effect of allele substitution. All of these are pretty much the same terms, but they're different from the genetic variants associated with the trait. So you must watch out for the terminology in these regards. Also note that univariate MiXeR model is quite simplistic. It's a simple spike and slab mixture of causal and non-causal effects. And it doesn't model the enrichments of gene sets, annotations, allele frequency, or LD-dependent architecture. Therefore, to some extent, polygenic overlap uncovered by MiXeR will partially reflect these common properties of genetic architectures. But as we observe low overlap in certain analyses, particularly between schizophrenia and height, we are fairly sure that MiXeR model does capture some unique properties of the phenotype in a cross-trait analysis. MiXeR also provides an RG estimates, but those are generally consistent with LD score regression. And for RG estimate, it's best to use the original software package from LD score regression or other packages designed to capture RG, because they put more focus on the accurate standard errors estimates for RG. And let me thank you for listening to this presentation, and also huge thanks to the PGC, to my colleagues, and to funding agencies. Let's move to the Q&A.